Acids and bases are important in organic chemistry because many chemical reactions are run in the presence of an acid or base. This tutorial will provide you with an overview of acid-base chemistry that occurs in organic reactions. You may recall the typical Bronsted acid-base equilibrium that occurs when a strong acid is placed in water. For example, when water and hydrogen bromide are mixed. We can write the chemical equilibrium below to illustrate that the lone pairs on the oxygen atom of water will remove the proton on hydrogen bromide to create a hydronium ion and bromide anion. The equilibrium is defined by the constant Ka. In this case, we say that the water is a proton acceptor and the hydrogen bromide is a proton donor. We define two different conjugate acid-base pairs. First, water and the hydronium ion, and then hydrogen bromide and the bromide anion. The equilibrium constant Ka is defined by the equation shown, which can be simplified to the concentration of the products on the right side of the equation divided by the concentration of hydrogen bromide. For this reaction, the Ka is 1.58 times 10 to the minus 9 molar. We normally don't communicate the strengths of acid in terms of Ka values, but rather pKa, which is defined as the negative log of the Ka. For this equilibrium, this computes to minus 8.8. Since these numbers are not in scientific notation, they're easier to handle, and it allows us to compare acid strength in an organic reaction. Those acids with lower pKa's are stronger acids and are more likely to be proton donors. The pKa values of some common functional groups are found below. While it is not necessary to memorize these values, you can start to see some trends that emerge. Knowing the rough pKa values for common functional groups will make understanding organic reactions much easier. You also notice that there is a wide range of pKa values, from strongly negative to well above 50. Remember that the pKa range is logarithmic, so a decrease in a pKa of around 2 is a roughly 100-fold increase in acidity. There are several factors that affect acidity, and some are more important than others. We'll go through those now. The first factor is bond strength. The better orbital overlap you have between atoms, the stronger the bond. In the case of acids, this means that it is less likely that a proton will be removed. For example, consider the hydrogen halides. The size of a hydrogen atom is very close to the size of a fluorine atom, so the orbital overlap between these two is quite good, leading to a strong bond with a pK of 3.1. Compare this to the very large iodine atom, which is quite mismatched in size with hydrogen. This makes the bond weak, and as a result, the pK is around -10. The second factor is electronegativity. More electronegative atoms can better stabilize the negative charge of a conjugate base. For example, if we look at the following 4 molecules and we were to deprotonate each of them, we would notice that the negative charge of the conjugate base would reside on a carbon, nitrogen, oxygen, and fluorine atom respectively. Fluorine is the most electronegative of all of those atoms, so it can better stabilize this negative charge. As a result, hydrogen fluoride is the most acidic of these acids. The third factor is hybridization. Atoms with greater S character hold electrons closer to the nucleus, which has a stabilizing effect on negative charge. For example, if we were to consider the molecules ethane, ethene, and ethyne from left to right, we will notice that the hybridization of the carbon atoms are sp3, sp2, and sp hybridized respectively. Since the sp hybridized carbon atom contains 50% S character, it is better able to stabilize the negative charge that results from the acid becoming deprotonated to form a conjugate base. Thus, ethyne is most acidic with a pK of 25. The fourth factor is sigma donation, or hyperconjugation. Bulky groups contribute electron density via their sigma bonds. This has the effect of destabilizing negative charge. For example, consider the following three alcohols: tert-butanol, isopropanol, and methanol from left to right. The pKa range of these molecules is quite small, but we can clearly see the trend that methanol is the most acidic. This can be explained by comparing the conjugate base of methanol, methoxide anion, to that of the tert-butanol, tert-butoxide anion. In order for the proton to be very acidic, the negative charge must be stabilized. In the case of tert-butanol, the sigma carbon-carbon bonds are more donating to the existing negative charge. This is destabilizing to that negative charge. On the contrary, sigma carbon-hydrogen bonds are less sigma donors. They're weaker sigma donors, and thus do not destabilize the negatively charged oxygen atom as much. As a result, the methoxide anion is more stable, and methanol is more acidic. The fifth factor, and a quite important one, is polarizability. Large atoms are more diffuse and are better able to stabilize negative charge. For example, take the molecules water, hydrogen sulfide, and hydrogen selenide. The pKa values decrease across this series because the negative charge that results from deprotonation is better stabilized by the larger selenium and sulfur atoms than the smaller oxygen atom. Inductive effects are also important to acid strength. Bond dipoles can help to stabilize negative charge through the sigma network. Consider the following series of acids in which acetic acid is substituted with an increasing number of chlorine atoms. Since chlorine is an electronegative atom that pulls electron density through the sigma network, we see a decrease in the pKa as the number of chlorine atoms increase. This is because when acetic acid is deprotonated, the negative charge can be stabilized slightly by inductive effects through the sigma network. And there is just simply more induction with trichloroacetic acid than monochloroacetic acid. The seventh and most important factor that affects acid strength is resonance. Spreading charge over multiple atoms, whether it's positive or negative, via the pi network is the most stabilizing factor of all. For example, consider the acids water, acetic acid, and sulfuric acid. The pKa values decrease across this series. The reason for this is that the conjugate base that forms upon deprotonation of acetic acid, for example, has two different resonance forms, or Lewis structures, that can be drawn. This has an incredibly stabilizing effect on negative charge, and it's as if each oxygen atom bears only a half of a full negative charge. The reason that sulfuric acid is more acidic than acetic acid is because there are three resonance forms, which is even more stabilizing. Now that you understand the factors that affect acid strength, let's see if you can practice ranking the order of acidity or basicity of various organic molecules. For the first question, rank the order of the following acids from most to least acidic. Next, rank the following bases from most to least basic. Remember that when comparing base strength, you're looking for ways in which electron density is destabilized, and the anion or molecule would pick up a proton that much more readily.